Se va a partir.
Para cuando me presentes también mejor si te pones aquí. No, simplemente estar cerca del ordenador.
Para
o sea, aquí
sí,
pero bueno, en YouTube solo esta página. No te preocupes. Vale, pues están comunicadas. Sí, cuando son y 31, cuando te consideres un par de minutos. Jairo, ¿te ha parecido ahí un cartelito?
Ya, este es el de streaming.
Cuando quieras.
Bueno, muy buenos días y bienvenidos a esta nueva charla de la serie de seminarios del Departamento de Física de la Materia Condensada. Hoy tenemos el placer de contar con nosotros con el profesor Jairo Sinova. Lo voy a presentar en castellano, aunque luego pasaremos a hablar en inglés, que es todo más fácil, pero como Jairo es de Valladolid, pues vamos a hablar castellano, incluso intentaré hablar un buen castellano. Bien, Jairo ha hecho toda su carrera científica fuera, se doctoró en el 99 en la Universidad de Indiana, en Estados Unidos, y después hizo varias estancias postdoctorales por allí en Estados Unidos también, en Tennessee y luego en la Universidad de Texas en Austin, y finalmente conseguiste una plaza de profesor en la Universidad Texas A&M en 2004. Y fue por aquellos años cuando, al menos cuando yo, el primer paper que recuerdo de Jairo, un Physical Review Letters, en el que proponía una vía universal, un mecanismo universal para spin Hall effect, spin orbit driver, ¿vale? Gobernado por la presencia de un acoplo spin órbita en semiconductores paramagnéticos, si recuerdo. Tras eso, bueno, ha tenido una carrera muy conocida en el mundo de la espintrónica y de la teoría de efectos espintrónicos, y desde hace unos años es profesor von Humboldt de física en la Universidad Johannes Gutenberg de Mainz. Y bueno, pues eso, volvió a Europa hace unos 10 años o un poco menos, ¿no?
Sí, 8 años.
8 años. Bien, allí lidera el grupo de teoría de espintrónica y sobre todo en los últimos años es más conocido porque lidera también SPICE, Spin Phenomena Interdisciplinary Center, que bueno, pues, lleva una serie de años organizando workshops y reuniones en torno a la espintrónica y que probablemente pues, se ha hecho todavía más famoso desde marzo del 2020, algo debió pasar en marzo del 2020, para que bueno, los seminarios online de SPICE del miércoles por la tarde pues son una cita mucho más conocida. Es verdad que SPICE pasasteis online casi inmediatamente y ha sido desde entonces un foro muy importante, ¿no? Un polo de atracción de la comunidad importante. Bueno, tiene varios premios, varios reconocimientos, lo que ya os he dicho, con Humboldt, es fellow de la American Physical Society, pero yo creo que lo mejor es que darle la palabra. And all yours, Jairo. Thank you very much for coming.
So if you don't mind, I will switch to English. There's no way, it would be very embarrassing for my mother, but there's no way I can give a talk, a physics talk in Spanish, because I would be translating in my head and everybody would laugh all the time. I tried one time in the Complutense and Autónoma one time, and then they started laughing at my Spanish, my physics Spanish, not my Spanish itself. I know que hablar un poco, pero la física es imposible. Okay. So today I want to tell you a little bit about a different story that we've been coming up with that also has occurred as it was said, know about spintronics, spin-orbit coupling, and things that you drive angular momentum through spin-orbit coupling, the mechanism that makes the charge degree of freedom and the spin degree of freedom talk to each other. And I'm going to turn that off today for you. I'm going to show you something that is even stronger at the level of exchange, the level of creating magnetism, and to show you that there is actually a new class of magnetism that was there, but we didn't see it, or how we saw it. Okay, and this is what I mean by this, the discovery of altermagnets. What do they actually mean? Sounds a little intriguing, but it's actually real. And then the nice thing is also been proven to be shown discovery-wise. But of course, at this stage now of my life, as it was discussed, I'm mostly just a figurehead now, the centers and things like that. So all of the work that I'm talking about is just I'm an advertising for very, very talented young people. Libor Schmeckel, these are all his ideas. So this is one of the things that I want to get it straight. Yeah, I am just learning from him, and most of this is his work that I'm talking about. So keep an eye on this guy. This is going to be a luminary of our field. And of course, my very long-time collaborator, with whom we share him as a PhD student, Thomas Jangworth, with whom I've been working now almost 25 years, as long as I've been married. Not to my wife, not to him, okay? That's too clear. We're married to different wives. So anyway, so thank you for having me here. It's wonderful. It's the first time in Zaragoza. I now live in Mainz, a little north of Karlsruhe. You've checked out what Mainz is now? No. On Google? Take a look, yeah? Anyway, so what is altermagnetism? I'm going to tell you what it is first, such that you have an idea where we're going. It turns out that this is an emerging third basic magnetic phase. Okay, we all know ferromagnets, you all know antiferromagnets. I'm going to try to convince you that altermagnets, which some of you may have thought of them before as a material, as an antiferromagnet, have actually, in fact, different properties, and you can distinguishably really break them up by symmetry, a very distinct barrier of the different classes and why they have different properties. They are compensated non-frustrated collinear magnetic structures, at least the ones that I'm going to talk about today. So if you just went by this, you would think, oh, that's an antiferromagnet, but they have a spin split, non-relativistic and correlated band structure. The spin split, as you will talk in a minute, is something that you would never associate with an antiferromagnet. You would always think that the band structure of the system is spin degenerate in an antiferromagnet. They have a different terminology of spin physics and electronics that
can be thought of from the ferromagnets. So this is materials that behave like one and both. And then it is, in this particular case, we now understand how to, by symmetry, identify them directly from the parent crystal material. They seem to be very abundant. I will show you that it's actually 1/3 of the magnetic classes belong to this. And they are also quite relevant to other fields. We're going to see why in a minute, and that we have to begin to explore. Okay. So I wanted to make it a little bit of a colloquium style, those are very basic. Please interrupt me anytime for questions. Don't wait until the end if there's something that puzzles you. I don't mind, I prefer that. So you know that in the colloquium you will say, okay, you have these atoms that have individual states, and as you bring them together, you create these bands, okay? But of course, these bands, you know, you don't have just bands that don't matter. In this case, the actual symmetry of the system matters. So how the atoms are arranged matters. And we know this because then in this case, you have in the state of matter, you have the crystal arrangements, and the momentum is a good quantum number. You have different bands. And in this case, the interactions are arising from the crystal environment, and the magnetic order, in this case, is not, of course, the dipole-dipole interaction whatsoever. It's really Coulomb interaction and Pauli's Coulomb principle that makes the exchange interaction very strong. It's a very strong interaction, tends to be the electron volts, and this is why, for example, iron, you almost have to melt it to actually get rid of magnetism, many of them. So it tends to be a very strong effect, a very strong energy scale of the order of the bands themselves. Now, in ferromagnets, you're used to, you know, we know this is the original ferromagnet, of course, a discovery thousands and thousands of years ago, but it has very important core physics, and one of them is that they are electrically active and magnetically active, meaning that most of the times in this case, you're going to have a split between the bands. So you have in this case, just depending on the orientation of the magnetization, the spin ups and spin downs bands of the majority bands will switch, and the Fermi energy tends to lie often, and for many ferromagnets, metallic. They have some ferromagnetic, antiferromagnets, but large fractions tend to be metallic. And this is what has made them very active materials. And this is actually, of course, where you have this, you know, I'm from Gothenburg University, so I'm bound contractually to tell you that this is the first analog sample that I can give you of going from analog to digital. So the digital analog, so the ink to spin revolution, it really happened around 2007 by the discovery of GMR and TMR, and then applications now to high density drives that we have, okay? And that is based on this core basic ferromagnetic physics, that you have these electrically active ones. Now, when it comes to antiferromagnetic, you know, you have also this important physics. You have anomalous Hall effect. This is the effect that in the presence of the magnetization being perpendicular to your sample, you have a very strong interaction, in this case, spin-orbit coupling driven, that will be a way to electrically detect magnetization. And you have, as I mentioned, is the one that created that ink to spin revolution, these TMR and GMR effects that now also form a spin transfer torque and giant magnetoresistance, give you magnetic random access memories as well. Okay. Now, when it comes to antiferromagnets, on the other hand, when Neil discovered them, or identify them before, you know, it was one of the curious things that antiferromagnets are one of the last order states that we identified. Superconductivity was identified way before antiferromagnets. This is the last one in the way, at least from the symmetry point of view. And they were noticing these funny ferromagnets or funny paramagnets with funny susceptibilities. And it was Neil that put together that in reality, they are just coming from this anti-aligned arrangement of the lattice, looking at in this case, the rutile, which he used, essentially the iron lattice fluoride rutile, where you can now, if you just focus on the magnetic atoms themselves, just from Kramer's theory from the 1930s, you can actually show that this would be essentially a spin degenerate band. There will be no spin splitting. This is because you have, in this particular case, just by looking at the magnetic arrangement, magnetic atoms, You have parity, meaning that they have inversion symmetry. Around this point, you can actually show that if you invert here and combine it with time, you will have this PT symmetry on these materials. And if you have PT symmetry, by definition, you will be a spin degenerate, because once you transform in your band structure, the spin up K will go to spin down K. But of course, because it is a symmetry of the system, that means that they have to remain the same. And then therefore, by definition, due to Kramer's theorem, they will be degenerate. So you end up with, in this particular case, electronically inert, so because most of the time they actually, the Fermi energy is in the gap, and magnetically inert, because you have zero magnetization. And it is curious that Neil, who actually himself was a very practical man, yeah, he's actually the one that came up with the idea and saved many, many lives by these ships that they were being destroyed by these magnetic mines, water mines. He realized that there was all kinds of magnetism when you bend the iron, and then you can actually, by putting wires around this huge wires, you can demagnetize them and save lots of people. So in this case, but he actually made an interesting statement that they're interesting, but they're not very practical. And this is why many people began to not focus so much on the practicality of this antiferromagnets for a long time, although they have been used, of course, in a static way to pin ferromagnets in the magnetic hard drives, but not in an active way. And then you have the question that you can ask yourself, why magnets that macroscopically demagnetize themselves so nicely for us, can we not use them actively? And this is what the field of antiferromagnetic spectronics has started. I mean, antiferromagnets has been studied for a long time, but the ferromagnetic spectronics refers to the active play of antiferromagnets, where we now try to electrically drive them, electrically address them, manipulate the magnetic order. Also, you want to actually use the fact that they have terahertz dynamics, so they're ultra fast because exchange interaction comes into play in their dynamics instead of the gigahertz that a ferromagnetic would have. They're, of course, the hard, there are many interesting aspects of it. There's also the aspect that there's many more in nature than the ferromagnets. Most magnetic order systems would prefer to be antiferromagnet than ferromagnet. Also, all of us in here, just as a point, you're all paying 15 euros, each of us in the world, per year for 4 types of magnets that are used in technology. Only 4. There's a lot more antiferromagnets, it turns out. Okay. And then I will not talk about this, but they have this possibility to the multi-stable neuron-like type of states. So there's a lot of interesting things and benefits about antiferromagnets. But which actually in 2014, this is another thing that we predicted in a particular antiferromagnet, which have it has broken inversion symmetry, but it's created with 2 sublattices that each have broken inversion symmetry opposite to each other. And with this type of material, manganese to gold in this case, which is still a PT antiferromagnet, the regular one that would be the spin degenerate, you can, by driving a current, you can switch the magnetic state. And they've got a lot of activity in trying to understand it. And then also you can control some of the topology. And then if you go insulated, you can go long distances. You can see the review here. But it seems that this is it. That there's kind of nothing else left, right? You either have an actively spin split ferromagnet or active, but a spin degenerate and inert type of physics. So you seem to just have this, you still have the idea that in these things here, you can still manipulate them. You have an electric signal because anisotropic magnetic resistance, you can still see it. And this seems to be what you have. You have net magnetization for the ferromagnets. It's used commercially, primarily with the spin splitting, which is the most important thing. The relativistic aspects of it are not used commercially so much anymore. For the research and development, they are, and the magnetic random access memories, they're using actually, so you could put a little green dot in there as well. But the antiferromagnets, from the active point of view, you have the idea there's not net magnetization, you can miniaturize them. There's no spin splitting, and you can both use relativistic physics to switch them or not, but most at the research stage. But if you actually start thinking, well, can I fill in the table a little more? This is where you can actually think, okay, what about what I love by symmetry? And to by symmetry, you're also allowed to have net magnetization 0 and spin splitting. There's nothing that prevents you that. And of course, you can turn on and off spin-orbit coupling. And the other possibility, which will be net magnetization and non-spin splitting, it turns out by symmetry, just by basic symmetry, not allowed, and there is no symmetry. So in this case, you only have to worry about, okay, do we have this? Okay, is that a possibility? Now, as I mentioned, if you just look at the magnetic atoms themselves here, if in the ferromagnet you have the spin splits, and in this one, if you just look at the magnetic atoms, you will think immediately that not just by Kramer's theorem, as I said, a mathematical theorem of symmetry, you don't have it. On the other hand, one thing that you should not forget is that this is not in a lattice by itself. It's embedded in an entire lattice. By this I mean that, for example, if you look at the antiferromagnet that has this type of structure, this rutile structure with this that has this 90 degrees between, because it now is decorated by non-magnetic atoms here in this rhombohedral structure. In here, the connection between the lattices is not anymore by inversion. It's actually done by a rotation and a change of color. Okay, here at 10 of the spin of the coupling, so the spin to me is just a color, plus or minus, not directional. Okay, and if you do that, it turns out that in this particular case, when the transposition, when I can translate one sublattice into the other one, connected by a rotation and a change of color, okay, then you will see, okay, I don't know what happened there. And then you will see that this is, in this case, you have alternating spin splitting in momentum space. So there is actually spin splitting. The total is zero in the Fermi surface, in the Fermi itself. But in this case, related by these degrees. Essentially, it's not within the same band, but it's the 90 degrees, this band will be split different from that band. You still have zero net magnetization like in the ferromagnet. You have a spin splitting, and I will show you that you actually have polarized spin currents that now been detected, which is something that you would associate with ferromagnets. And they have, of course, ferronic magnetization. Before, they would have to be identified simply as antiferromagnets. But of course, actively, it would be an interesting aspect to them that we can do. And they're quite different, for example, from the spin splitting due to spin-orbit coupling. If you have a spin-orbit coupling, you actually have this time reversal symmetry not being broken by the spin-orbit coupling, and then you have these chiral states themselves. In this case, the splitting that you see here, essentially in this particular case that I'm showing you of the rutile, is the spin ups and spin downs. They're rotated by 90 degrees, these ellipses that you see here. Okay, it's a real bunch of, in this case, the ruthenium oxide is a real calculations. Okay, so you end up, just as I mentioned, this is the first slide that I showed you already, of these properties that you will see by this material that the antiferromagnet, collinear antiferromagnets per se, they have this collinearity of the two spin ups, but in this case, in the crystal environment, the two sublattices are connected by a rotation, okay, and a change of color. And they will have these properties that I already mentioned before at the beginning of the talk. So first, I'm going to talk about now the first three to show you what is the physics that make them different, okay, that we can predict and show. And then afterwards, I will spend the last part of the talk about the symmetry, how by symmetry, by thinking of what is called spin symmetries instead of magnetic symmetries, we can identify them by looking at the crystal symmetry of the system itself. And why is the reason why it was not identified before? This is one of those things that really, once we actually put it together, you think this should have been in the textbooks in the 1960s. But there's a reason why not. And it has a human tendency to follow what we've done before and what we learned from our predecessors. Yeah. So let me spend some time now showing you these aspects of why how they are, what is the different physics that you see that is different from an antiferromagnet. First of all, let me show you how the exchange is actually, how this splitting is occurring. And in this case, I'm going to use our workhorse that we're using is ruthenium oxide. This is rutile. In this case, this oxide rutile is metallic. It was shown to be metallic, an collinear antiferromagnet not too long ago, only a few years ago. And in this case, in the presence above the nail temperature, you have this band anisotropy due to this local inversely symmetric electric field crystal field. that distinguish this. There's a split in the bands between A and B sublattices. Okay, and then once you turn on the spin-orbit the exchange, what happens is that you're going to have this. Of course, the spin-ups and here designed by color. The two bands A and B with different band colors, but the split in itself is opposite in the opposite sublattices. That is what is effectively happening in this case. So you end up with an exchange split, with a spin splitting that is very unique. Essentially, this A and you have the A and B sublattices from the spin point of view. It is actually mirroring the crystal field. But of course, because in this case, the exchange is much larger than the crystal field splitting, in this particular example, this will be a very different symmetry than any spin splitting you've seen before. Okay. But it's, in this case, rather large, to the point that, as I mentioned, the spin splitting are gigantic compared to the spin splitting that you will see from a spin-orbit coupling in this case. And in this moment, and it will be in this case momentum-dependent exchange splitting. Compared to the ferromagnet, typically it's just a constant. You just shift one band and the other completely. In this case, it's going to be momentum dependent. This, how it depends on the momentum, it relates to how what is the rotation symmetry that you need to do to actually connect one sublattice with the other. Okay. For this one, this case is a D-wave type of symmetry. Now, what are the consequences that you have? Well, the minute that you have these bands like this, as I showed you, here's the Fermi surface, where you have here the spin ups and the spin downs, and you drive a current in this way, for example, you will see that this is a polarized current, okay, just from the density of states. That's a very simple calculation. And you can actually calculate, as we've shown here, in this PRX this year, that you will have also a very large giant magnetic resistance and tidal magnetic resistance of over 100%. If you manage, of course, to control the different domains with opposite chiralities. But because you have also this very large anisotropy of the spins, if you actually notice now, you can actually do what is called exchange splitted. If instead of running the current in this 110 direction, you run it in the opposite, in the 100 direction, you will notice that in this particular case, the spin ups and the spin downs in this direction cancel each other out, so it's unpolarized current. But you create a very large spin current perpendicular to the driving current. So this is like a spin splitter in a sense. It's not a spin Hall effect because it's not driven by spin-orbit coupling. Okay, it's not a Hall in that sense. But in this case, it's huge. And actually, the spin Hall angle that you would get in this case is close to 30%. So just by looking at the physics, the spin Hall angles tend to be very small because spin-orbit coupling tends to be small, tend to be of a 1%, maybe 10% at best, but really is 1%. Most paramagnetic materials, and then you can enhance it by other ways of interfaces, but very difficult. But if you look at material was, if you do this fast machine or this high throughput DFT calculations of 35,000, 40,000 magnetic material or paramagnetic materials, and see what is going to be the strongest spin Hall angle, you go from 1% to 2%. Yeah. But by thinking of these physics, you go from 2% to 38%. A very large number. Not only that, we actually put this prediction in the PRL of last year, and then only a few months after, the team in Cornell by Dan Ralph observed it. And now it's been published in Nature Electronics just in May, actually beginning of this month. Okay, you can see the experiment. So this already has shown you that these are not fake. You have an antiferromagnet that is generating this very, very large spin polarized currents. Okay, in this case, pure spin currents. And this is why we're calling it altermagnets. Of course, it's nice that it's alternating exchange, spin splitting, but because we don't know what to call it. Do you want to call it antiferromagnet because it has zero magnetization, because anti-aligned, the way you would use to identify, or do we identify with the core physics of ferromagnetism, which is having spin splits and polarized currents, which you don't have in antiferromagnets, and then in the PT regular antiferromagnets. So this is actually just to mention, by the way, in this case, this whole angle itself is dissipative, like it's actually proportional to the conductivity. So there's a conductivity measurement, and as I mentioned, depending on the strength of the disorder, is quite large. And I wanted to also mention this collaborator in Colombia, not only Libor, that did this work itself. And as I mentioned, it beats 20,000 conventional spin-Hopf materials. Okay. Now, another one that you will see from the core physics that we saw in ferromagnetism, remember, we have GMR and TMR, that's core physics of ferromagnetism. You also have anomalous Hall effect. Now, in this case, the anomalous Hall effect does arise by turning-on spin-orbit coupling. But before, you would have thought also by symmetry in a PT symmetric antiferromagnet, just by definition, you will not have anomalous Hall effect because essentially pseudovector is not allowed to exist. In this case, you actually do have it. By symmetry is also allowed. It's called the crystal anomalous Hall effect, as and has now been observed in 2 experiments, and both in this case with lithium oxide and manganese tellurium as well. And so you can have, if you want to, there's a different talk in itself. I can, talk about that later for anybody interested. And there, the difficulty is how to identify the orientation and the reorientation of an egg order to identify the anomalous Hall effect correctly. Okay. But in this case, it's observed as well. So this is why I'm saying that now you have these core physics that are from ferromagnetism and some static physics that are from antiferromagnetism material. But that's why we're calling it a different name. Okay. Now, in order to call it a different magnetic class, if I want to call it a class, I should actually identify by the symmetries. And this is why it's important now to talk about the symmetries and what really convinced us that it was independent, that it was not just simply some funny anomalies of antiferromagnets, that you can distinctly break out the classes by a symmetry point of view. And then the question is how to do it. That's at the time. It's 45 minutes, right? Don't worry, it's not going to be too long. And then, you could think of, okay, what about the useful way that you would actually do in magnetic classes, as Landau really taught us from the beginning, was to say, well, it's natural to take the orbital magnetism and the spin and couple them together, because they actually originate due to the same effective physics. And once you couple them together, that means that any operation, symmetry operation that you do on the lattice, on the real space, you will do on the spin space. So if you do a rotation of the lattice for 90 degrees, you have to rotate your spin by 90 degrees. That is the magnetic symmetries. Okay? Magnetic group symmetries and magnetic symmetries. Now that's what this is. And you can see all the magnetic tables, Professor Litvin. But then in this case, you would miss a lot of this physics. Okay? Because here, you will have splittings that are allowed, but you cannot distinguish whether they are from a ferromagnet, from the spin-orbit coupling or exchange. You don't have a way to split it because they are coupled. And actually, in case magnetic symmetries, an antiferromagnet and a ferromagnet will belong to the same magnetic group. You will actually have to do the calculation to tell whether it's a ferromagnet or antiferromagnet, because many of them are allowed to be in the same magnetic class because they are coupled. It's, it doesn't, it's blind to disentangle many of these magnetic phases that we're used to. Okay, that's one thing that people don't quite believed it. That they thought, oh no, if I take all of the symmetries at once, it will get there. Well, the problem is that you've coupled everything, including something that is a small scale compared to a large scale, which is exchange. And then, yeah, of course, we will break the symmetry, but it's a very small broken symmetry that you will miss. So you want to have what is called exchange symmetries or something that dominates. And in this case, this was not, it was already actually developed, but not really exploited in the 70s. This spin is what's called a spin symmetry groups, where you treat real space and spin space separately. It's a vast generalization of the magnetic groups, but no magnetic group will actually belong to the spin group, because the spin group itself has properties that only rotate and operate on the spin itself, which you could never do with magnetic symmetries analysis. Now, why is this important is because with this, we can then begin to identify the rotations themselves, because here in this, when you actually separate the two, you can identify collinear ferromagnets and collinear antiferromagnets directly by the spin rotation symmetries.